was having some issues with my computer a minute ago, so we'll see if it's sped up at all. I can handle this linear regression a little bit better than it was. So let me just make the font a little bit bigger so you can read it. Okay, so the idea behind linear regression is we're going to have a set of data points. Let me just put the data points right here onto my graph paper real quick. So maybe I've got one at 1, 4. I've got another one at 5, 9. And then I have another one at 9, 13. So when I look at these three data points, what I notice about them is that if my goal is to draw a straight line through those points, I can probably get pretty close at doing so, right? If I tweak the y-intercept of my line to be just so, I can kind of get it to mostly pass through those 3 points. If I can furthermore tweak the slope a little bit, maybe I make it 1.2 instead, maybe adjust this down, I can kind of get a little bit better with each of my successive guesses. But what you notice is that no line that I can draw is going to exactly go through all 3 of these data points. And so either I have to give something up. Either I have to forget one of these data points, in which case then of course I can draw a straight line that passes exactly through any 2 of them. But I would much rather not do that if I can avoid it. So we can either forget all but 2 data points, but a better way to approach this problem is to choose a line that, and I'm going to try and say this as carefully as possible, choose a line that gets as close as possible to as many of the data points as possible. So I want to think about what that actually means here for a second. So if I think about how this, let me make it a different color so it's a little bit easier to see. If I think about the way in which this red line gets close to or doesn't get close to these 3 blue points that are right here, there's some error that's involved, right? This actual linear equation model is getting close but not quite to each of these different points right here. For example, when this red line passes through the x-coordinate of 5, its y-coordinate is 5 times m plus b, right? If I plug a 5 into my y equals mx plus b equation, 5 times m plus b, it passes through the point 5, 8.7, whereas the point itself has coordinates 5, 9. So that difference between the y value of the data point and the y value that the equation predicts, that difference is what we call a measured error, right? And so along with that comes a, let's see if I can do this, a measurement error of, so I'm going to do 8.7 less than or equal to x, less than or equal to y, less than or equal to 9. And then we're going to do this from x going from 5 to 8.7 minus 9, minus 8.7. Let's see. Does that actually do what I wanted it to here? Not quite. I wanted 5 plus that. There we go. So if we sort of zoom in here, I've just drawn this little teeny tiny square. And the area of that square, the bigger that square is, the more error that there is in between my measured value and my actual value for my data. This 8.7 is 5 times m plus b. So let me just make that adjustment here. So this is 5 plus 9. That's going to be 14 minus 8.7. That's 5 times m plus b. All right, so the point is that if I put this line in different spots, the amount of error by which it misses that point at x equals 5 is going to be greater or smaller, depending on how far away it is. And this line that I happen to place right here, this one that we were trying to take as our candidate, has a pretty small amount of area that's in between there. There would be a similar little teeny tiny area square for how much error exists at the point on the left and also the point on the right. So the whole point, the whole purpose of trying to fit the best possible line, the principle that we follow, is the principle of minimizing what we call the squared error. That would just be the sum of all the areas of these little error squares. And that squared error is just going to be a function of the slope and the intercept that I choose. So as soon as I choose a slope and an intercept, I'm going to get a line that might have more error relative to my data set, or might have less error relative to our data set. And if the fates are kind, and mathematically and statistically we can prove that under most reasonable circumstances they are kind, there is a unique line that minimizes the squared error. And that's going to be the one that best fits my entire data set. Right? It gets as close as possible to as many of my data points as possible. Well, how do we find that? Really, finding that equation is a statistical process, or even a sort of an analytical process. You might use some calculus tools to actually discover what is a formula. How do we take all the data points into consideration at the same time to find an equation for a line that best fits as many of the data points as it can? Fortunately, we can almost always use technology to short circuit that calculation. So I'm actually going to jump ahead and we're going to look at how to do this process using Desmos. So we'll do that right now. And then we'll also, afterwards, take a look at how to do it with spreadsheet software. So we'll look at how to do it with Excel. I may also do it with Google Drive as well, because that's a nice cross-platform tool. So how do we use technology to find an equation for a line of best fit, a linear equation that gets as close as possible to as many data points as possible? So in Desmos, it's a fairly straightforward process. Once you have your data set in place, so step one is enter your data set into a table. The way that I have over here on the left side, right? All my x values in the first column, the y values in the second column. Then, what I like to do is I like to just write down the model equation. And what I mean by model equation is like a template. You're basically telling Desmos what kind of equation are we going to try and fit to this data. And at this point in our course, the only model equation template that we have familiarity with is the template for a linear equation. Y equals mx plus b. So I'm just going to write that, y equals mx plus b. If I just write that in Desmos, what it's going to do is it's going to give me the opportunity to add sliders, which is what we were doing before, right? If I add these sliders, then I can slide this m value around, I can slide this b value around manually, and we can investigate some different lines. But that's not actually what I want to do, because I want Desmos to be the one to pick not just any slope and intercept, m and b, but the best slope and intercept, m and b, to best fit the data set that we have. So if I want that to happen, what I'll do then, in my third step, is I need to tell Desmos where the y's and x's are coming from. So replace x and y in the Desmos model equation with the names of the lists in the table that have that data. So that'd be x1 and y1, just because, whoops, I'm running off the screen here. what I want to make sure happens is I want to make sure Desmos is referring for these x and y values back to the x and y values that are part of this particular data table. So rather than y and x, I need to write y1 and x1. Except now it's gobbled up my data, so let me go back and add my data back in. Actually, I should probably make that not the third step, but the fourth step. My apologies. Let me nudge that down. Erase my 3. That's going to be step 4. Because if I do that too soon, the way that I did here, it is just going to gobble up my data. I don't want that to happen. So instead of doing that, what I want to do at step 3, and this is totally a Desmos thing. This is not something that would show up on your written work on an exam or something like that. But this is just the symbol that you use to tell Desmos that you're looking for a regression. Replace the equal sign with the Enye twiddle sign, this little twiddle that's usually it's on your keyboard above the back tick mark, which is usually somewhere to the left of the number 1 on your keyboard. So I'm just going to replace that equal sign with this twiddle sign. That little twiddle sign is what's going to tell Desmos we're looking for a best fit equation for this data. And then I'll change y to y1 and x to x1. Whew, there we go. So now my data is all still intact, and Desmos is now showing me graphically, it's showing me a line drawn on my graph paper over here, and that line appears to very closely match the 3 data points, and because it's the line of best fit, it matches those data points better than any other line that you or I could draw on this XY plane. And so that's the process for finding a regression, a regression on a given model equation using Desmos. And what we get out of this is a whole lot of information. And I want to kind of take apart some of what that information is telling me. So out of a regression, we're going to get several things. First of all, we're going to get the regression equation. And that regression equation we can find just by taking the parameters, so the value of m and the value of b that Desmos has spit out for me here. And we just put those parameters back into our model equation y equals mx plus b. Right? So y equals mx plus b, but Desmos has given me a value for m and it's given me a value for b. M equals 1.125 in this example, b equals 3.0416, I'll just round that to 0.42. Right? So these parameter values substituted into my model equation, y equals mx plus b, then gives me this equation, y equals 1.125 times x plus 3.042. And as always, the slope and the intercept of this equation are things that we can then interpret in the context of the problem, whatever problem we happen to be working on. If it comes out of an applied context, we can put an applied spin onto what the slope and the intercept mean. For example, this 3.04167, the value of b, that's my y-intercept, my vertical intercept for this line. And so we find that exactly at that point right there, that point at which the line intersects the vertical axis. We'll have a y-coordinate equal to that value of b. Similarly for the slope, 1.125. That's telling me that for every 1 unit of distance I go to the right on my line, I have to go up vertically by 1.125 steps. This as a fraction would also be equal to 9/8. And so for every 8 that I run, I would have to rise by 9. And so it looks on this graph as though the point 9, 13 looks like it would go exactly through that point. Maybe this is also rounded off a little bit. Doesn't seem to quite line up exactly, but pretty darn close. Okay. So that's how we get a regression equation out of this process. But there's one more piece of information that we get out of a regression calculation that's important to mention. and that's called a correlation coefficient. And Desmos gives it to us in two different ways, but what these two numbers are going to tell us. Correlation coefficient kind of tells us how strong is the model, how closely, I'll try and write this over here, how closely does the line match the data? So if I'm looking at my graph here on my XY plane, it seems like this line, you know, qualitatively at least, it seems like it's mostly capturing the trend that's evident in the data. Like my data points are not too far away from this line. So just from a naive layman's perspective, I would look at this line and say, you know what, that's a pretty good model of what this data is doing. It's not missing the mark by a huge amount as it passes nearby the data points that we started out with. And the way that the correlation coefficient communicates that information, let me kind of make some space up here for this, is it communicates it with a number. And that number is called, first of all, R. So R is called the correlation coefficient. And R is always a number between -1 and 1. -1 and +1. But it can exist anywhere along the spectrum in between -1 and +1. Right? And at both ends of that spectrum, at the +1 end and at the -1 end, we get what are called perfect linear correlation. A perfect match when R is equal to +1, and a perfect match when R is equal to -1. In both of those cases, the line that we draw goes exactly through every single one of the data points. So if I start out with a data set that already is exactly modeled by a linear equation, then the correlation coefficient we get out of that linear regression is either going to be +1 exactly or -1 exactly. And the difference between those two cases is the slope of the line. So when the correlation coefficient is +1, that means that the perfect linear match is going to have a positive slope. So in the example we're looking at right now, our regression equation does in fact have a positive slope. The slope is equal to 1.125, right? And my graph, my line, is increasing as we go from left to right on our graph. If R were equal to -1, we'd be talking about a perfect linear match that has a negative slope. So at both ends of the correlation coefficient spectrum, we get perfect match between the equation that the regression model comes up with and the data points themselves. The line that we get would exactly pass through every single one of the data points at those ends. And then there's everything in between. And of course, most regressions are going to fall somewhere on that spectrum in between -1 and +1. And we can kind of think of R equals 0, this point at the middle, as a point where sort of all bets are off. There is no linear model is better than any other. So there's a situation where a linear equation really doesn't fit this data well at all, because any linear equation we could write down fits this data just as well as any other linear equation that we could write down when R is equal to 0. So there would seem to be no linear correlation at all when R is equal to 0. And so the closer that we get out to the ends, the closer that we get to +1 on the positive correlation side, the closer that we get to -1 on the negative correlation side, the stronger that the association between our quantities happens to be, and so the better that our equation fits our data. So in the example that we're looking at here, Desmos gives us a value for R. We get it from right here. R equals 0.9979. And so what I can do, what I can observe about that, is it's very close to +1. right? Positive 1.00, if you like. And so the fact that it is very close, quote unquote, means that we're going to have a strong correlation. And the fact that it's very close to a positive 1 says that we have a strong positive association. Strong positive correlation between x and y. That this data are very well modeled by this increasing slope linear equation that the regression spit out for us. So that's one way in which correlation coefficients get reported as the value of r. The other statistical artifact that comes out of a regression is what happens when I take that number and I multiply it by itself, 0.9979 squared. That r squared value, 0.9959, is another type of correlation coefficient. It's called the coefficient of determination. R squared communicates the same kind of information, except instead of a spectrum from -1 to 1, R squared exists on a spectrum from 0 to 1. After all, if I take numbers between -1 and 1 and I multiply them by themselves, the result is always non-negative. It is always going to be between 0 and 1. And so again, at one end of the spectrum, at the one end of the spectrum, we have a perfect model. Now I'm writing underneath my graph again. Let me scoot that off to the side. On one end of the spectrum, we have a perfect model when r squared is equal to 1. On the other end of the spectrum, when r squared is equal to 0, we have sort of no correlation. No linear model is better than any other linear model. And so the closer that r squared gets to 1, the stronger the correlation that the linear model is giving us. The only reason to prefer r squared over r is that it has a more concrete statistical interpretation. This tells me what percent of the variation in one of my variables is attributable to the variation in the other. In other words, how much of the association between these variables is being captured as a signal, like a real, true something to believe by this regression, compared to the noise, the variation in one of my quantities that's not explainable by a variation in the other, according to this model. So in this example, 0.9959, which another way to understand that number is that it's 99.59%. 99.59% of the variation in y is attributable to the variation in x. So there's only, less than 0.5% of the variation in one of these quantities that's not explainable by the variation in the other. So we've captured almost everything that there is to know about the relationship between x and y just in this one simple model equation. That's what the correlation coefficient of 99.59% is telling me. So when I ask you on a quiz or an exam to tell me about the strength of association or the correlation coefficient, as long as you are clear about which of these two you're reporting, I don't care if you use r or if you use r squared. Either one is fine, and depending on what technology you're using to actually get your information, some tools like Desmos give you both of those things right off the bat. Other tools like Excel tend to only give you one of those two. And so that's what I want to do to wrap up our session today, is look at how to do the same kind of process using different types of technology. Before I go there, let me take a quick 15-20 second break. If you're watching us live and you have questions you want to see me address in this back half of our streaming session today, please contribute them into the Slack channel or into the Twitch chat. I'm just going to take a quick 20-second break and we'll come back and look at how to do this using spreadsheet tools, Excel and Google Drive. So now that we know the basic contours of what linear regression is, how do we use different kinds of technology to accomplish a linear regression? Desmos is great as a free online tool. It really, for me at least, has completely replaced graphing calculators in my life. And it's much less expensive. It's 100% less expensive to use than a graphing calculator. But you know, the situation usually warrants, when we're doing this kind of work out in the real world, particularly in the workplace, spreadsheet tools like Microsoft Excel or like Google Drive are usually the tools of choice because they can handle larger data sets. They can do a lot more than just the sort of the graphing and the graphical based regression analysis that Desmos can do. So let's take a minute and look together at how it works in a sort of a honest to goodness spreadsheet. So what I'm going to do is open us up some Excel. So let me take those things off of my stage and add my Excel window on here real quick. Just bear with me. Excel, here it is. Now, a quick caveat on this is that I'm using the Macintosh version of Excel. I believe it's Excel 2013 or something like that. So your interface might look a little bit different. There are some reasons to prefer the PC Windows versions of Microsoft Office Suite software compared to the Mac versions, which sometimes have less functionality. Not just sometimes, I think they generally have less functionality. But hopefully this will be a valuable sort of, most of the step-by-step is the same in either case. So all I did here was I just opened a brand new workbook inside of Excel, and I'm just going to put in my data set. Just going to enter them into cells as columns, just the same way that we did it in Desmos. So my data was 1, 4, and then it was 5, 9, and 9, 13. So I put in my data points just into columns. We could have used rows if we want to. The Excel is pretty flexible about that kind of thing. So if I want to come up with a scatter plot, if I just want to plot these 3 data points on a XY coordinate system, the way that Desmos did it, the way I can do that with Excel is by, first of all, just highlighting this data table. And then from my insert ribbon, or you could also use the insert menu at the top of your screen, but I'm going to use the ribbon because we can see it more easily in this video. Just choose to insert a chart, and there's a whole list of different chart types I can use over here. The kind I want is a scatter chart, sometimes called an XY chart. So depending, you may have to dig down and find that. Right here is the button on my Excel system that will do that for me, an XY scatter chart. And when I choose that scatter chart, I want to choose it to not connect the dots. So I'm clicking right now on the version of a scatter plot which doesn't connect the dots one with another. So it's not already trying to draw in a jagged line for me. It's just plotting these 3 points as they are. And so right away what emerges is this picture that looks just like what we had on Desmos a few minutes ago. Excel has kind of tried to helpfully add a chart title that I don't particularly care about, so I'm just going to click on it and delete it. So here it is, but how do we get the linear regression information? How do we actually get Excel to tell me what is the linear equation that best fits my set of data points? To do that, we need to tell Excel, prompt Excel to do a linear regression. And there's a couple ways to do that. One of them, the way that I usually recommend to people if you're not particularly comfortable working with Excel functions, is to just right-click. So use the right mouse button to click on one of the data points in my chart over here. And it doesn't look like it's showing up in my video, but what I get is I get a, I'm just going to write this down over here. So right click a data point and then choose an option that says add trend line. So when I do that, add trend line, what it's going to do is it's going to draw in my case it happens to have drawn it in as a dotted line here, don't really care, whatever. It draws in my dotted line, and that dotted line is the linear regression, the graph of the linear regression equation that we saw from Desmos a little while ago. One of the things you'll notice it also does is it gives you an option of different types of trend lines we could choose. So right now, linear is the model that we prefer. But as we go into next week, we're going to be talking about exponential models as well. And so when those are appropriate, we can use those instead. But if we actually want to do anything analytical with the equation that we're working with, we are also going to want Excel to display the equation and also display the correlation coefficient, the R² value. And there is an option down here at the bottom in these checkboxes to do both of those things. So choose to display the equation on the chart, and sure enough, it pops up with this trend line equation. This is exactly the same one that Desmos gave us a few minutes ago. And likewise, display the R² value. So remember how I said that some tools will give you the value of R, some of them will give you R², some of them will give you both. Excel is the kind of tool that gives you only a value for R², 0.9959. So just take care that when you're interpreting that value, that's the percentage of variation in Y that is attributable to variation in X. And now we have a complete linear regression done in Excel. So that's my favorite way of doing this. Select options 2. On the one hand, we want to display the equation, and then also display the R² value. And that's usually enough to get us to what we need to do. The other way of doing this is to use Excel spreadsheet functions. For example, if I just want to know what is the slope of my linear association, what I can do is use an Excel function called appropriately slope. I can get that by choosing the insert function. It's this little FX button up here. And in my formula builder, I can just type the word slope. This gives me a function called slope that if I insert it, it's going to then prompt me for where are my Y values and where are my X values. So I'll come in and highlight my Y values right here. I'll highlight my X values over there. So the first argument to the slope function are my Y values, the second argument are my X values. And when I press done, the number that ends up in this cell right here is exactly the slope of the best fit line that we got from the linear regression. There's my 1.125. Similarly, if I wanted the y-intercept, I can use a spreadsheet function called, again appropriately enough, intercept. I type intercept, insert that function into my worksheet. It's again going to prompt me what are the y values that we're working with, and we'll highlight that range of y values. What are the x values that we're working with, and I'll highlight those x values. And then it gives me the value for my intercept. So I can also achieve a linear regression by doing it that way, sort of one coefficient at a time. And if I want my R² value, there's one more worksheet function. This one's unfortunately not called R², but it is called Pearson. Actually, I'm sorry, Pearson is not the R² value, it's actually the R value. So let me fix that as soon as I've gotten the first array and the second array. So my X values and my Y values, drop it in there, and this is actually my R value. So if ever you want Excel to give you R instead of R², you can use the Pearson worksheet function to do that. Pearson here is not the textbook publisher, but rather the statistician that first constructed this thing. But so that's another way that you can use technology. And actually all of this, all these functions and all the functionality that I've shown you how it works in Excel also works in Google Docs. So if you don't have Excel, if you have just Google Sheets done online, the very same process can find a linear regression there as well. So the purpose of all of the work this week is just to introduce this tool as a way to help you to plug in the skills and everything that we knew from last week about how linear equations and linear models work and how to interpret a slope and an intercept in an applied context, how to access all those mathematical skills from within a context of working with big sets of data for which we really need some technology to be able to boil them down into their essence as a linear model. So what you should be able to do now at the end of this week is to take a large set of XY measured data and discover a linear correlation equation that best fits the trend in that data, and then to be able to discuss to a broad audience of your peers or people reading the newspaper or other mathematicians or whomever, to be able to communicate the meaning of the slope, the meaning of the intercept, and then also, and this was the new thing this week, what the correlation, the strength of correlation, strength of association, the value of R or the value of R², what that actually tells you about the nature of the fit of that linear association to the data set that it came from. So I hope this was useful. We're really getting down to a place in the course where we're trying to take some relatively straightforward mathematics that you probably remember from your mathematical past and be able to connect it with some larger context of the world around us. How do we use technology to get us from very large questions about big sets of data down into these really nice sort of manageable, pure mathematical abstract models that we can use, and be able to use the latter to draw conclusions and make explanations about the behavior we see in the former. So we're going to continue this process as we move from this week into next, just making the kinds of models that we work with a little bit more complicated. We're going to move forward from talking about linear equations this week to talking next week about exponential equations and ways of modeling behavior where, rather than have a constant amount of change per unit time, for example, we're going to have a constant percentage of change per unit time. So exponential models are going to be a way of modeling a different type of change behavior in a relationship between two quantities. And that's where we're going to go with next as we move into next week's material.